Okay. All right. So recall a bunch of stuff. Okay, so we talked about in our products, we have used in our products in certain cases, right? So let's say we have a linear transformation, right? In such a way that there are elements in B okay, all right, and then we have a bunch of results as far as inner products are concerned, which is the first thing is that there is a symmetry property. And if you take a course on infinite dimensional function spaces, which are very, very crucial to understand how most of the deep learning algorithms work these days and why they don't work, okay, you will revisit these properties. And I'm just assuming that my vector space is spread over just real numbers. Okay, I'm not considering complex numbers at all. All right. Okay. And if you take the inner product of a non-trivial vector with the zero vector, you are going to end up in zero. All right. I mean, you know that inner products are nothing but a number, right? So it's a projection of one vector onto another vector. Okay. And if you project a vector onto itself, you actually get the length of the vector back. Okay. All right. Okay. Now we'll have to recall a bunch of things. So the second thing that we recall is that
So property number 3, it will be TV or T transpose V.
The T transpose, not transpose, it will be T square complex conjugate, right? But I am just considering vector spaces over real numbers. So T star or T complex conjugate is just T. Okay. So maybe you are right. You're right. So it's just over the real numbers. It's just T transpose. You're right. Okay. Thanks. So the characteristic equation, we all know, you would probably use this and many times, is that determinant of lambda minus AI is equal to 0. And as I said last time, that we are going to see why this makes sense. I mean, why do we take the determinant of this polynomial? This is a polynomial, right? Lambda minus AI is a polynomial, right? Why we take the determinant of a polynomial and set it equal to 0, and why does it actually give us the eigenvalues and the corresponding eigenvectors? Okay, you probably, I mean, nobody probably told you. You are just used to doing the algebra, right? Okay. And so in the context of this, it is very, very important that we recall null space of a linear transformation and range of a linear transformation. Right? Okay. So that's the point number 3. Okay. You should also recall that what exactly is a linear transformation? A linear transformation has an additive property, which is, which means that if you take, so we recall linear transformation properties as well, which is T is a linear transformation between vector spaces U and V in such a way that and there is a scalar alpha. Okay. It should also be obvious to you that if you map a zero vector, it should take you to a zero vector. Okay. All right. So with this, we also know, since we are talking about null space and range, we know that this guy is actually a subspace of U, okay, and this guy is a subspace of V, and that's easy to see, right? Okay, all right, all right. And therefore, if both U and V are finite dimensional vector spaces, the dimension of the null space of T would be less than or equal to the dimension of null space of U, and dimension of range of T would be less than or equal to dimension of range of V. Okay, dimension of V, sorry. And also, any subspace of a vector space by default contains the zero vector. Okay, all right, it has to have. Okay, so and then we recall the rank nullity theorem, okay, that we just briefly mentioned. We are not in a position to prove that theorem yet, right? But we'll just mention this. So, and this is, this is closely related to the concepts of null space and range, right? So the rank nullity theorem is that if you have a linear transformation where VU is finite dimensional, right?
Sir, I had a doubt. Excuse me.
Yes.
In the first point, you have defined the inner product on v cross V, right?
Yeah.
And you have defined it as inner product of U comma V is U into T of V.
U into U comma V. No.
Like basically the second point of the first point. What does that say?
No, that is U transpose. I'm sorry. It is not TU. Inner product of U and V can be written as the transpose of the first element of the inner product with V. That's obvious, right?
So this is a particular inner product that you're defining?
No, actually, look, inner products are, what is a dot product? If you take two vectors x1 and x2, right? Let's say let's take two vectors x and y, and x is x1, x2, and y is y1, y2. When you take the dot product of x and y, what do you get? You get x1, y1 plus x2, y2, right?
Yeah.
That's yeah. So what is x1, y1 plus x2, y2? Isn't it the transpose of x times y?
Right.
Yeah, that's it. Okay. So maybe what I should have done is that, because I agree that probably I should use a different notation for transpose, because you might get confused with the notation that I'm using for linear transformation. Okay. So this comes straight from multiplying one vector with another vector. Okay. All right.
Okay.
Okay. Clear. It's obvious, right? Yeah.
What about those vector spaces when you cannot define a transpose, or basically they are not matrix-like vectors?
Like, what do you mean? Given any column vector, I can always take the transpose of that column vector, right? It becomes a row vector.
So are you? Is it that all vectors can be represented as the column vectors?
Yes, I mean, if any vector can be represented as a vector. I mean, see, if look, what happens is row or column, it depends on how you represent it, right? So if you are looking across the rows of a linear transformation, which is matrix, you are looking at a row vector, but you take the transpose of it, you make the row as a column, right? So yes.
I mean, what about those vectors like 1, x, x square, x cube, this 4-dimensional vector? I mean, you will represent this as uh,
Well, what you are talking about is a
shapes?
vector space of polynomial functions. That's a different ball game. There your basis is different. There your basis will be 1x, x squared, and so on. Okay, all right. So I'll come to that. So there the way you represent things is different because that's a vector space over polynomial functions.
Okay, so we are talking about here the matrix type matrices as a base, right?
Elements of a matrix, because mostly we deal with the data, right? And data is discrete, and the way we represent the data is in terms of a matrix.
Yeah.
Okay. But hold on to that thought. It's a good question. I mean, I haven't yet talked about those type of vector space representations. I will do that. Okay. All right. But not yet. Okay. We are not ready yet.
So characteristic equation is a minus lambda I, right?
No. I mean, you can write it in any way. Just hold on, okay? You can write it in any way you want, okay?
Yeah.
All right.
Okay, sir. Okay.
Lambda is a scalar
At least.
matrix.
Yeah, at least. Pardon me?
Lambda is a scalar and a into I is basically a. It should be lambda I equal to a.
Lambda I minus r, right? You're right. Sorry. Yeah. Lambda I minus a. Okay, hang on. That's fine. So this is lambda I minus a.
Sir, just one more doubt. In the first point, how are the inner product and the linear transformation related, or are they not related?
No, they are not. What I mean to say is that you can take the inner product of linear transformations as well. Like for example, I mean, you can take the inner product of vectors. You can take the inner product of linear transformations because T of U is nothing but an element, right? So you can sometimes you require these kind of representations when you try to prove stuff, like the one that I will prove today, where I show that the eigenvectors, if the set of eigenvectors are linearly orthogonal to each other, then they are linearly independent. Okay, so there I will need to apply. So this is just the algebra of it.
Okay.
Yeah. Okay, so all right, guys, shall I go ahead? Yeah. Okay. All right. So I think this is the rank nullity theorem we were talking about, right? So if the rank nullity theorem says that the dimension of T is nothing but nullity of T, which is nullity of T is nothing but the dimension of the null space of T plus the rank of T. Okay. Now, what is rank? Rank is nothing but the dimension of the range of T. All right. Now, you also would recall that if your vector spaces, both U and V are identical vector spaces, and both are Rn, then you actually are looking at, so your dimension of V is nothing but n, right? And then this is nullity of T plus rank of T. So one of the implications of this is that if your linear transformation of the corresponding matrix is full rank, if it's a full rank matrix, which means the rank of this linear transformation is n, then you have n over here, n on the left hand side, and that would imply what? That the nullity of T, or the dimension of the null space of T, is 0. Okay, which means what? The only vector that the null space contains are the 0 vectors. All right. How does it matter? Well, it matters in the following sense, that suppose you are solving a system of homogeneous equations. Let's say T of V is 0. Okay, this is a system of homogeneous equations, and you are interested to know if there exist non-trivial solutions for such a system. You will not be able to obtain the non-trivial solutions of such a system if your rank of T is if your matrix is a full rank matrix. Okay, because your nullity becomes 0. Dimension of the null space of T becomes 0. So the only solution that you will get out of this system of equations is the trivial solution or the 0 solution, which we know anyway. Okay, so that's one of the implications of rank nullity theorem. There are other implications as well. If you recall that I said, yes.
In the statement that you've written to the right side, the first statement is it's if, right? If u equal to v, and if u and v are both n dimensional, then the statement below that.
Where?
If u and v are both n dimensional, then n is equal to nullity dimension of like nullity of T plus.
Yeah. That's what it means, right?
Yeah,
U v equal to
Yeah.
I'm sorry, guys. I'm just getting slightly better at whiteboarding. I haven't used this before, so sometimes I trust me. I'm just waiting for my blackboard to arrive, and the moment I get the blackboard, I'm going to switch it to a blackboard mode of class, and there you see my handwriting is not as awful as it appears here. Okay, all right. So, all right, okay. So this is the rank nullity theorem, and the implications. One of the implications of rank nullity theorem is this. Now, see, as I said before, all these machine learning and computation and modeling came into picture. It was a classical problem for a lot of people to figure out, if given a system of equations, how do I solve it? Do I really solve it by hand? That is absolutely infeasible, right? So now when you look at system of equations, there are different ways of looking at system of equations. You could have a system of non-homogeneous equations, which means that your matrix vector representation of such a system is TV equal to C, where C is non-zero. Okay, in such a case, what can you say about the properties of the coefficient matrix or the corresponding linear transformation that would ensure that you have a trivial solution or a non-trivial solution? The same thing applies when you try to solve a system of homogeneous equations, where you try to look for trivial or non-trivial solutions. Okay, it turns out that all of these answers to all of these questions can be beautifully answered using the concepts of linear algebra and linear transformation without having to dirty your hands in actually trying to solve the system. Okay, so the importance of this class for all of us to understand is that given a system of equations, do we know if there exists a non-trivial solution? That's it. We are not interested in actually computing those solutions, because you feed that to MATLAB, MATLAB will find it for you, or for that matter, any of the linear algebra solvers, right? But what we are interested to know to begin with is that whether such a solution, non-trivial solution, exists. So the existence is more important rather than actually finding those solutions. Okay. All right. So we did this, right? We just mentioned this. As I said, I'm still not going to. I'm still not going to talk about how we prove this theorem, right? But so the next one is that we need to recall subspaces, right? Since I said that null space of T is a subspace of U, and the range of T is a subspace of V. So what exactly is a subspace? It's a subset of a vector space with two properties that it has to satisfy, other than the fact that the subspace has to be non-empty and contains a zero vector. The one property is that closure under addition, and the second is closure under scalar multiplication, right? So if you claim that null space of T is a subspace of U, you have to be able to show that it satisfies those two properties, and the same thing applies to range of T. Okay, all right. Okay, now I think I should also give you an example, or rather just talk about it. Is that, let's say I have a bunch of scalars, A, B, C, D, all belonging to the set of real numbers. And I also know that their product is not equal to 0, right? And then I define a space. I define a space H in this manner, that it contains an ordered quadruple of vectors, right? And this obviously has to be a column vector 4 by 1 such that ax1 plus bx2 plus cx3 plus dx4 is equal to 0. Okay, so this is how I define this space. Okay, all right. Now you know that R4, the one over here, R4 is a vector space, right? Because we know that Rn is a vector space, so R4 is a small version of Rn where the basis vectors are 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. These are the basis vectors, and therefore the dimensionality of the vector space is 4, and that's why R4, right? Now the question is, can we verify that H, the question is H a subspace of R4, right? Okay, and if the answer to this question is yes, then can we find a basis of H? Okay, all right. Can we find a basis of H? Okay, before I proceed to this, guys, can I ask you a question? Do you know what a basis is?
Yeah, it should span and it should be linearly independent.
Right. So it's a spanning set. So if I give you any spanning set, let me ask you another question. If I give you a spanning set of any length, do you think it can be reduced to a basis?
Yes, if they are not linearly independent.
Yes, yes. So it has to be linearly independent. That's why I use the word reduced, correct? Okay, all right. Also, let me ask you another question. Okay, so let's look at this particular linear transformation over here. Let's look at this particular linear transformation over here, right? And I'm assuming that the dimensionality of U and V are different from each other, and I'm also assuming that both are finite dimensional, right? Okay. I'm also assuming that the dimension of V is greater than the dimension of U. Okay, all right. Now, my question is, if I define a basis set in U, if I define a basis in U, or if I'm able to find a basis in U, what is the relation of that basis in U to the vector space V?
Image of that basis will be a spanning set.
Spanning set of?
It goes from U to V, right? Then V.
Right. Spanning set of what? Spanning set of V?
The range.
The range, yeah, the range.
It could be the range. Anything else? Now, guys, since V is finite dimensional, let me rephrase my question. Let's make it more clearer to you. Since we know that V is finite dimensional, V also must have a basis, right? Yes or no? Speak.
Yes, sir.
Talk to me. Okay. So U is finite dimensional, U has a basis. V is finite dimensional, V has a basis. And I have a basis set in U. Now my question is, how does this basis set relate to the vector space V? Other than the fact that, I mean, it would be part of the range of V. Yes, I understand that. Or more precisely, how does the basis set in U relate to a basis set in V? Is it too difficult?
So could you repeat the question once, actually?
Okay. T is a linear transformation from a finite dimensional vector space U to a finite dimensional vector space V. U has a basis because U is finite dimensional. V also must have a basis because V is also finite dimensional. Now, the basis set in U and the basis set in V, what is the relation between these two? Okay, can I say this? And I will prove this later. But can I say this? The basis set in U can be extended to a basis set in V. Can I say this?
Yes, sir.
Yes. Why?
So
Yeah.
like one doubt, like like is it possible for like the mapping of the basis set of U to V, like some of them could that set need not be independent? Is that possible?
No. Yes, of course. Which is why I said, look. I mean, okay. Let me further clarify this. So let's say the dimension of U is M. Okay. Okay. Let's say the dimension of V is N. Okay. Let's also assume that N is greater than M. Okay. All right. All right. Now, so I define a basis set in U, U1 through UM. Can I do that? Yes, right? Okay. Now, my question is, can I extend this basis set to a basis set in V? By extension, what I mean is I need to have more vectors in it, right? Because since the dimension of V is N, and since N is larger than M, I need more vectors in my basis set, of course. Right, and then I need to investigate. Let me finish. I need to investigate that the new set that I created, U1 through UM. So let's say I now have created a new set, U1, UM, and V M plus 1 through VN. Okay, all right. I have created this set. Now, I need to ensure two things. One is that this particular set spans the vector space V, and this particular set is also linearly independent. Okay, if I'm able to satisfy both of these conditions, then the answer is yes, I will be able to extend the basis from U to a basis in V.
Sir, one question.
Yes.
You've written here like the set U1 to UM and then VM plus 1 to VN. But yeah. U is from a vector space of a different dimension, right?
Yes, that is fine.
But VM and like VM plus 1 has like a higher dimension. So like that set doesn't have the same.
No, but like see the VM plus 1 to VN, these vectors are not in U. These vectors are in V. Okay, so this whole set is in a vector space V, and this particular subset is only exclusive to V. They are not in U. Yes, go ahead.
Is V a subset of U?
Which one?
Is V a subset of U?
No, the other. V is a superset of U. The other way around.
The mapping is from U to V, right?
Yeah.
So V will have to be a subset of U, right?
No, why? It could be either. It could be both ways. I mean, if I had written it the other way around, which means that M is greater than N, then I would have meant that the dimension of U is greater than the dimension of V. Guys, this is just relate to a system of equations where you have two possibilities. Your number of variables is greater than the number of equations, or number of equations is greater than the number of variables. Both can happen, right? Okay.
Yes.
So yeah, so this is just equivalently represented as T goes from U to V. The dimension of U can be greater than dimension of V. In that case, what will happen is that the length of the basis that you define in U has to be greater than the length of the basis that you define in V. But in this case, it's the other way around. The dimension of V is greater than the dimension of U, right? Which means the length of the basis that you defined in V has to be greater than the length of the basis that you defined in U. That is why that is the reason you need to extend your original basis U1 through UM to U1 through UM plus VM plus 1 all the way up to Vn, because your total number of basis vectors in the vector space V has to equal to n. That's how you compute the dimension, right? How do you calculate the dimension of R3? Why do you say that the dimension of R3 is 3? It's because you know that in R3 the basis vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1, a spanning set which is linearly independent. How many such basis vectors? 3, and that is why the dimension of R3 is 3. Okay.
Excuse me, sir.
Yes.
The images of U1 to UN in V, their linear independence is trivial, right? Because if alpha 1 U1 plus alpha 2 V2 is that satisfied, then the transform of that will also.
Exactly. Very good observation. But that does not guarantee that the extended basis that you have created in V will also be linearly independent. You have to show that. You have to verify that.
Yes, sir, because we're adding more vectors on top of
Correct.
Okay,
Correct. Exactly. Okay. All right. Okay, guys. All right. Good. No, I'm really glad that you are asking these questions. Okay. I'm really happy. All right. So shall we move on to the
just one doubt. The
sure.
set that you have written U1 to UM and then VM plus 1 to VN.
Yes.
So it shouldn't be U, right? It should be the transpose, the image of U1s. Because U has a smaller dimension than.
No. That is the only. This is the basis set, guys. I mean, when you are mapping U1 through V, it is definitely T of U1, T of U, T of VM. But this is just the basis set. Okay. All right. Now, shall we move on to this particular example, subspace example? Yes. You have any more questions? No? Okay.
So can we make a statement that if U1 to UM, VM plus 1 to VN are linearly independent, then can we say that it will form a span for V?
Yeah, I mean, but you have to first, no, but you could have a linearly independent set. Like, for example, in R3, right? I mean, in R3, you could have 1, 0, 0 and 0, 1, 0. These two are linearly independent of each other, right? Okay, but does these two form span R3? No, you need another vector.
Here the dimension of the set is n, right, and the dimension of the vector.
No, right. But I mean, this is as of now, this could just be a spanning set. Okay, until we prove that this spanning set is also linearly independent. So it's not imperative, it's not trivial, you have to show it. Okay, and while showing this, you use the properties of linear transformation, which someone has rightly pointed out.
Okay.
Okay. All right. So shall we move on to subspace? Okay.
Yes,
right.
sir.
Yes. Okay. All right. Great. So the subspace example, because I just needed to show one example to you, right? Okay. So now, what happens is, I mean, you notice this different. Now I have to save this first, and then I'll have to erase this, right? So let me do that. Lecture 4. All. Okay. I wish there is a way to copy paste, but anyway, probably I'll figure it out later. Okay. All right. So I guess I have to write this again. So we are discussing point 4, which is A, B, C, D. They are in spread over the real numbers. And then there is also, we know that A, B, C, D a product is not equal to 0, and we have defined a vector space H, okay, which is x1, x2, x3, x4, such that ax1 plus bx2 plus cx3 plus dx4 equal to 0. Okay, so the question is H a subspace of R4? Sorry, this is 4. Okay, this is, and then what is the basis of H? Damn. Basis of. Okay, all right. So how should I proceed this? I'll just take two elements from this subspace, from this vector space H, right? I'll take H1, okay, which belongs to H. Now, since H1 belongs to H, it must have the same representation as H, right? So, which means I can just pick up ordered quadruple, right? Okay, all right, such that ay1 plus by2 plus cy3 plus dy4 equal to 0. I'll take another element from H, H2, right? And let me call this Z1, Z2, Z3, and Z4, such that the same property is satisfied. AZ1 plus BZ2 plus CZ3 plus DZ4 equal to 0. All right. Now, what do I need to show in order to show that H is a subspace of 4? That since H1 belongs to H, H2 belongs to H, their closure, the additive closure, they should have an additive closure, right? So H1 plus H2 should also belongs to H. Now H1, so see what happens is H1 is given by this, right? And H2 is given by this. So when you take the sum of this, it's obvious that it's 0 plus 0, right? And that is 0, right? Okay. Similarly, I take just an alpha, a scalar, okay, all right, and I look at what is alpha H1. What will be alpha H1? Alpha H1 will be nothing but alpha times AY1 plus BY2 plus CY3 plus DY4, and you know this is 0, so this is 0 as well. Okay, all right. So all we had to show that if two elements are in H, then their additive closure, I mean their addition is also closed under in H, and the scalar multiplication also, we have the same closure property, right? Okay, all right, and therefore H is a proper subspace of R4. H is a proper subspace of R4. Okay, the next question, the following question is, what is the basis of, or can we find a basis of such a vector space H? Okay, all right. Now I take an arbitrary vector H1 which belongs to H, right? And I know that the way it looks like is Y1, Y2, Y3, and Y4. That's the way it looks like, right? Okay. Now what I can do is that this is a trick that is standard and is followed across, is that, you know, I mean, try to reduce the number of entities in the ordered quadruple representation. So, I mean, given this particular equation, right? Given this particular equation, the way this subspace is defined, I can express Y1 in terms of Y2, Y3, and Y4. And since I have only one equation, I do not have a choice. I can just do it once, right? So would you agree that I can write y1 in this following manner? Minus b by a y2 minus c by a y3 and minus d by a y4. I'll just replacing y1, right? So that I just reduce the number of basis vectors. And the second entry is just y2, the third entry is y3, and the fourth entry is y4. Okay, now this can be written in the following manner, right? I'll just, instead of writing minus b by a, let me just call this k1, minus c by a, let me call this k2, and minus d by a, let me call this k3, sorry. Okay, so would you agree that I can write this as, or rather not minus, just assume that b by a is k1. So minus k1, so let me take out y2. If you take out y2, then you have minus k, right? k1, comma, 1, comma, 0, comma, 0, plus y3. What happens when you take out y3? It will be minus k3, comma, 0, comma, 1, comma, 0. And if you take out y4, then you will end up getting minus, sorry, this is minus k2, I'm really sorry, minus k3, comma, 0, comma, 0, comma, 1. Okay, so take a minute to just to verify whether I have made any algebraic mistakes. I don't think so. Okay, but let's just look at this. All right, so I mean, what are your candidates? So these are scalars, right? The y2, since you have pulled it out, these are just scalars, right? Okay, and your candidates for the basis vector are these, right? These are your candidates for the basis vectors. Okay, all right. Now, it remains to be seen is that are these vectors spanning the set? Are these spanning the set? Do they span the set? The answer is yes. Are they linearly independent? By any means of visual inspection, can you tell me whether these guys are linearly independent or not?
Sir, yes, sir, because there's one in unique places. So
correct.
If
one is actually you are applying a right shift operator to one, right? You're just using a right shift of operator to one, so one is getting shifted, right? If that were not the case, what would have happened? You would have been able to express one of these vectors as a linear combination of the other one, and there goes your linear independence out of the window. So yes, very good. Who was that?
Sir, me.
Me as in I don't see you. What's your name?
Sir, Sanjay.
Sanjay. Yeah. Good, Sanjay. Good. Okay. All right. So therefore, yes, it forms a subspace, and the basis of the subspace is these three guys. Okay, because it's a spanning set as well as linearly independent. Okay, good. Okay, I just had to show one example. So let me just save this. And just so you know, I'm uploading all of these whiteboard material to the class drive. I have created a whiteboard folder. Okay. By the way, before I forget, I posted another assignment, and that's not due any soon, right? It's due on September 21st, right? Okay. But that assignment has a condition. First of all, don't upload this to the homework folder. Okay. The TAs will pass out an instruction of how to upload your solutions. The second one, that assignment problem, that homework problem has to be solved using one method only, and that method is specified. in the assignment itself. Okay, all right. If you solve this problem using any other method, even if your solution is correct, I'll have to give you 0. Okay, I just wanted to make make sure of that. All right. So let me get rid of this. Okay. So we recalled the definition of a subspace with an example of a subspace, right? Okay. All right. Now, once again, we come back to the same question that are we able to answer questions like, sorry, I mean, are we able to answer questions like systems of solution to system of equations? Okay, trivial or non-trivial solutions, trivial. And at this point, recall that if your matrix is a full rank matrix that comes from the rank nullity theorem, then your null space only contains the 0 vector, which implies that a system of homogeneous solutions will only give you the trivial solution. Okay, all right. So with this in mind, let me talk about a very nice property of a null space. It's a very, very nice property. All right. So it is our second theorem of the class. I think we proved one theorem before, if I'm correct, is that let's define a linear transformation from V to W. And then what I claim is the following, that T is injective. Do you know what injective is? One-to-one. Okay. If and only if okay, all right. So do you understand the meaning of if and only if? It's a necessary and sufficient condition. Okay, all right. Now, before I prove the theorem, let's talk about why do I care, right? The question is, guys, any idea? Can anybody throw some light on this? I'm not proving this first. I'm just, talking about this.
Sir, if it were injective, then you could make a statement about the dimensionality of like U to V. I mean, V to W.
I'm assuming these are finite dimensional. Well, if the vector spaces V and W are both infinite dimensional, all your linear algebra rules fail. I mean, you can't handle these using linear algebra. You'd have to, use ideas of Hilbert space and stuff like that. And that's a different course. This has some connotation in the context of system of equations. Okay. I mean, I'll try to help you. What happens if, what if T is not injective?
So then you won't have like a unique solution to like.
Why? If T is not injective, then your null of T is not equal to 0, right? Okay, if your null of T is not equal to 0, then you go back to the rank nullity theorem. If your null of t is not equal to 0, that means what? The null space itself contains vectors which are other than 0, isn't it? Right? And therefore, when you are trying to solve a system of equations TV equal to 0, system of homogeneous equations, this guarantees that the such system of homogeneous equations will give us non-trivial solutions, which we are interested, because anyway, when you multiply a matrix with a vector Ax equal to 0, you know that by default the solutions that you are going to get are trivial solutions. We are not interested in trivial solutions. What we are interested in is that if such a system of equations have a non-trivial solution, right? So if your null of t is not an injective map, it actually gives us non-trivial solutions to system of homogeneous equations. Okay? It gives us non-trivial solutions to system of homogeneous equations. Now I really want to finish non-trivial solution to system of homogeneous equations defined by Tx equal to 0. Okay? All right. Now, so now that is the idea is clear that why we care about such results. Okay? Let's see whether we can make sense. Okay? All right? Let's say if we can make sense of such a statement. I mean, in the context of some abstraction. Okay? If you notice carefully, you will see that I am doing most of these things without actually invoking matrices. Okay, all right, and that's the whole point of this course. Okay, all right. So let's see this quickly. I think I have some time, and I'm also facing a challenge that you guys are joining 5 to 7 minutes after the class starts, and so I'm losing 5 to 7 minutes every day, right? So let's try to make up some time today. Okay, at least 5 to 7 minutes. Okay, all right. Okay, so you know how to deal with this if and only if type of thing is? So there is both directions that we need to show that this is true. So first we assume that t is 1 to 1. Okay, t is 1 to 1. So this is in the forward direction. I'm going in the forward direction. Okay, we assume that t is 1 to 1. Okay, now we also know that null of t. We know that the null of t is at anyway, guys, I won't bother. I think you know what I want to write. Subspace of V. And therefore, by virtue of null of t being a subspace of V, null of t must contain the 0 vector, right? Okay. Okay, all right. And we know that by virtue of the linear transformation property that if you map 0, if you apply a linear transformation to the 0 vector, you will be mapped to 0. Okay, all right. Now the question is t is 1 to 1, right? We know that t is 1 to 1. Now what that means is if I choose another non-zero vector in null of t. So if I choose another non-zero vector in null of t, right? Then by the definition of the fact that V is in null of t, I will have this PV equal to 0, isn't it? Right? Because this is the definition of null of t. Definition of null of t. This is how null spaces are defined. So what do we have now? We have t of 0 equal to 0, and we have tv also equal to 0. Right? So we have two different vectors. We have two different vectors, right? And you apply the same mapping, and two different vectors are being mapped onto the same object. Is this possible? Under the assumption? No, right? Because why? T is 1 to 1. So T is 1 to 1 meaning what? I mean, for every input, the mapping has to be to a unique output, correct? So two identical input cannot be mapped to a single output. You know this from the definition of one-to-one functions, and this isn't any different. So therefore, what happens is, what will happen is, this cannot happen. This cannot happen. It implies that there does not exist such a vector E, non-zero vector belonging to null of T. Which means what? The only thing that null of T contains is the zero vector. All right, so this is one way. This is one way. Okay, what is the other way? I don't have a space here, but so I'll just try to squeeze it in over here. Okay, what is the other way? Other way is the other direction, right? This direction. What is this direction? That this direction is that I will assume that null of T equal to 0. I will assume that null of T equal to 0, and I need to show that T is 1-to-1. Okay, all right. Now, so this is given now. So in this direction, this is given. Okay. Now let's just say that TU equal to TV. You know how to show a function is 1-to-1, right? You take T of X and T of Y. You assume that T of X is equal to T of Y, and if you are able to show that that implies X is equal to Y, then your function or the linear transformation is what? 1-to-1. So we will do exactly that. Okay, but in this case, the T is a linear transformation. So what I can write here correspondingly is the following: that T of U minus T of V equal to 0. Okay. Now, by virtue of the properties of linear transformation, you know that this is T of U minus V can be written as T of U minus V, right? Correct? This is a property of linear transformation. And therefore, what else? Right? This implies that U minus V belongs to null of T. This is the definition of the null space. What does this imply? And we also know that null of T equal to 0, right? So the only thing this U minus V has to be equal to is 0, which implies U equal to V, and that implies that T is 1. Okay, that's it, guys, for today. Thank you.
Sir, if you don't mind, can you go back to the previous slide once?
Previous slide?
Yeah, the previous
I mean, the
board.
previous
Yeah,
slide.
previous board.
Okay. Hang on.
Yeah.
Which is null of T inductive. No, wait a minute. For subspace example. Yeah, you mean this one?
The recall board.
Recall board. Okay. Yes.
Here, can you, I just wanted to clarify the third subpoint of the first point once again. I am still confused what is happening in the third point.
You mean the TUV is U comma T transpose V?
Yeah. Like I'm not, like, can you just change the notation a bit?
So that's it. That's okay. All right. me see what I can do.
So T on the LHS TU is the linear transform. And on the
Right.
RHS you have V transpose U. What do you have on the RHS?
U, comma, T transpose V.
T transpose V.
Yeah, that is because
Okay.
we consider the vector spaces over reals. If we consider the vector spaces over real as well as complex spaces, then this T transpose will be replaced by T complex conjugate.
Right. So, because our vector space is defined our reals, the linear mapping is just a matrix of real numbers.
Correct.
Okay, and but a third property is non-trivial, right? It seems a bit complicated.
It's not trivial. That's why I wrote it, right?
Yeah, but we'll have to prove this, right? Like I'm not understanding how this happens.
Yes. We have to. Okay.
Okay.
Right?
So
But
we'll prove it later.
That's a separate discussion on inner product spaces.
Okay.
Yeah.
Thank you, sir.
All right. Okay. Yeah. All right, guys. Okay. See you on Friday.